now we're going to look at the second part of the course. Sorry we're going on a little bit late today. We've got about another half an hour to go. Now I want to talk to you about VSDs, variable speed drives. Are any of you familiar with VSDs? Have you installed them or worked on them before? Okay, we've been asked to include the VSD part into our course by the manufacturers because, unfortunately, VSDs are wonderful things, but people have been installing them wrong, and that's caused all sorts of problems. So let's have a little look at VSDs and the various things about them. Firstly, controlling speed has always been something we've wanted to do. One way we had of controlling speed was by having one big shaft that ran throughout the whole factory, and that shaft was run by probably the steam engine, and then when each section of the factory would take a drive off of that section. Now, even if we were controlling something like sections and sections of conveyor belt, you always get slightly different slippage, slightly different resistance, slightly different friction in each part. So we've been needed to control the speed. Now, John, I'm going to get to the point about the specialist because it is a very valid point, and we'll be getting to that in just a little while. So, the nice thing about speed control is that you can alter the speed ever so slightly. Now, when we went to electric motors, one way we had of doing this was to use an MG set. Now, I don't know if any of you have ever seen the type of MG set I'm talking about here. I'll try and draw it quickly. What we had was a big old DC motor, and that was driving a shaft. And on that shaft was a whole bunch of conical pulleys. And on the other side of things was another conical pulley, and each one of those was attached to an AC generator. Okay, so there was a belt running across there and a belt running across there. And then each AC generator was directly coupled to an AC motor. So each AC generator was directly coupled to an AC motor. Now, by altering the speed of the main DC motor, we would speed up and slow down all the AC generators, which of course would speed up and slow down all the AC motors. And by moving the belts backwards and forwards, you could speed up and slow down individual sections. So that's one way we had of doing this. It was called the MG set, the motor generator set. Now, the reason we used a DC motor is because it's very, very easy to change the speed of a DC motor. That being the case, why don't we just use DC motors here? Why don't we just use DC motors? Why do we bother using AC motors when DC motors are very easy to speed control? Yeah, AC motors produce more torque for their size, and they've got less stuff inside them. Basically, the rotor part of an AC motor is a chunk of iron. There's nothing inside there. There's no brushes, there's no slip rings, there's no commutators, there's nothing to go wrong in them. all you've got is a bunch of coils, and they really shouldn't go wrong. Well, I know they do, but they don't go wrong as often as the brushes and stuff. DC motors are a pain. They're a maintenance pain. And on top of all that, you've got to generate DC to feed them with. So we prefer to use AC motors whenever we can. Here's an exploded diagram of an AC motor. The important parts of an AC motor are the rotor, this bit, and the rotor, as I've said, is just a slightly elaborate chunk of iron. Another very important part of an AC motor is the fan. The fan is essential, that 50-cent piece of plastic. Yeah, you're right, you can use AC for braking, regeneration. Yeah, you can do all sorts of fun things with AC. You can actually do that with DC as well. Now, other things that I need to draw your attention to are the terminal box. The terminal box is made up of a lid and a main part, and in between the two, there's a gasket. Pretty obvious, really. And at this end, there are bearings, and at this end, there are bearings. These are the important parts of an electric motor, an AC motor. Just here, there's a set of coils. Okay. We feed an AC motor AC, alternating current. Alternating current is generated by rotating a magnet inside a set of coils. So what we have is we have a magnet, and we rotate that past a coil. And when we rotate a magnet, this is a shaft, when we rotate a magnet past a coil, out comes AC current. Funny things happen with AC current. When we create AC current, back here we create an AC, we create volts. We actually create volts. Voltage is pressure. We create volts, and those volts push the amps. So we create volts, and the volts, which is the pressure, push the amps. Now, if you put volts and amps across a resistor, nothing much happens. The volts are reduced and the amps are reduced because there's less pressure there. If you put volts and amps across an inductive load, and an inductive load is a coil. Anything that has inductance. So anything that has a coil and a chunk of iron associated to it. If you put volts and amps across an inductive load, what happens is that the current and the voltage go out of phase with each other. What we say is, and I'll have to write this down, I use civil to remember. Right, we say that for an inductive load, inductance is L, for an inductive load, the volts leads the current. And the more inductive the load is, the more inductive loads there are, the more the volts lead the current. Now, the problem we have, the way we describe this is using a thing called the power factor. I'm sure I'm preaching to the converted here. I'm sure you all know this stuff, but I just want to go through it all again. We have a thing called the power factor, which is actually the inverse tan of the angle between the two. But basically it's a number, power factor, and it's a number between, well, it's a number 0 to 1. When the two are perfectly in phase, we have a power factor of 1. When the two go out of phase, as the inductive load goes up, the power factor becomes smaller and smaller. Now, we're not, if we put a big inductive load on there and we have a power factor of, oh, I should have put a point in there, 0.9, what that means, put simply, is the motor's now running 90% efficient. If we have a power factor of 0.8, the motor's only 80% efficient. To make the motor, to get as much out of the motor, we need to put more into the motor. We need to put 120% as much energy in to get the same amount of energy out, because the motor's running less efficient. It's only running 80% as efficient as it should be, because the two are out of phase. That's kind of what power factor means. Now, Western Power have dictated that there's only so far we can push the power factor. Does anybody know what the maximum power factor change we're allowed to have is? Yep, 0.8. You're not allowed to push the power factor beyond 0.8. Because the problem is that when you put a big motor on your line and you shift the power factor, you also shift the power factor in the mains. And so you kill everybody else's motors. Well, you don't kill them, you make everybody else's motors run inefficient. So the more motors we have, the more we affect the power factor. And we want to maintain a power factor as close as possible to 1. Luckily, capacitors push the power factor back the other way. So a capacitor is a capacitor, makes the current lead the voltage. So if we put a capacitor in to match every inductor, then we will keep the power factor around about 1. So what we have in big plants and big mine sites is a big machine called a power factor corrector. And basically, it's a bloody great big cabinet full of capacitors. Has anybody ever seen this? Of course, on a small scale, we do the very same thing inside a fluoro. We have a capacitor and a fluoro to correct for the choke we've got inside it. Now, even if it's a small box, how much noise does it make? It makes a humming noise. That's my wife just bought me a nice cup of coffee. Anyway, it generally sits there humming and buzzing to itself. The reason it's humming and buzzing is because it's full of capacitors and they're humming and buzzing. The other thing is full of fans, because the damn thing tends to get hot. Now, there's a hint there. It's using power. It's not free, this thing. We're using power to correct for the power factor. So it's a little bit expensive to buy, and it's a little bit expensive to run. That's the first thing I need you to consider when we talk about motors. Now, we use three-phase power. Any ideas why we use three-phase and not six-phase or two-phase or single-phase or what? Why do we use three-phase? Yeah, it turns out that three phases is the minimum number of phases you need in order to ensure that the motor goes round always in the same direction. It also turns out that it's the most efficient when you start considering things like cables, the number of coils, and it's the most cost-effective, I should say. But mainly we use three phases because it's the minimum number of phases that will ensure the motor always goes round the same way. Okay, so we're using three phases.